All right. So let's do this first problem. Find the equation of the plane containing the point 2, -3, 6 with a normal vector or perpendicular vector if you prefer, n equal to 4, 5, -3. Or if you prefer, n equal to 4i plus 5j minus 3k. Either way. Okay, the fastest way to do this is to do the following. Our equation, our coefficients of x, y, and z are just going to be the components of the normal vector. So it's going to be 4x plus 5y minus 3z equal to some constant. And the way we find that constant is by plugging in the point that has to be in the plane. So plug in the point 2, -3, 6. We're going to get 4 times 2 plus 5 times -3 plus -3 times 6 equal to our constant. So that's 8 minus 15 minus 18 is going to be -25. So our equation is going to be 4x plus 5y minus 3z equals -25. That's it. Right. There are other ways to do this, but this is the best way. Let's talk about projections. We'll probably get to that question, but we got to talk about some other stuff first. Let's talk about projections. I'm a little ahead of my notes here. 1 second. Projections. So as the name would imply, if you've got two vectors, and I'm going to draw a picture here, I like this notation better. So if this is my vector u, and this is my vector v, then, or let me actually draw it this way as well. This is my vector v, this is my vector u. The projection of u onto v is just the vector you get when you kind of drop a perpendicular from u to v. Oh, why are you all unscrewed like that? So 1 second here. So if I drop this down like that, make a right angle there, this new vector that's in the same direction of v, that vector there is the projection of u onto v. Or in this other situation here where the angle between them is greater than 90 degrees, we're going to extend v in its opposite direction here and drop this perpendicular down that way. And this vector here is going to be the projection of u onto v. So both of these are the projection of u onto v. And then, for whatever reason, I do not love this particular notation, but it is standard, so we got to live with it. The magnitude of the projection of u onto v is called the component of u onto v, and written as the component of u onto v. I do not know why this is called this thing. I feel like it's a terrible name, but that's what it's called. So just the magnitude of the projection. So I'm going to start off by trying to find this projection vector by first just finding its length. So we're going to find the component of u onto v, just equal to the length of the projection. All right, let's use some trigonometry here. So let's call this angle theta, this angle theta. And here's what we're going to say. We're going to say that, well, I'm going to say that cosine of theta is equal to the length of the projection, aka the component. Gosh, you feel like they could have come up with less cumbersome notation, but it's pretty gross, yeah. Divided by the magnitude of u, aka the hypotenuse. So there's the cosine of theta, right? Adjacent over hypotenuse. Here's something I've noticed over the years. If you see a cosine you're dealing with vectors, it means you probably need to make a dot product appear. So I know that the dot product of u and v, right? You all know the dot product of u and v. One way of thinking about that is the magnitude of u times the magnitude of v times cosine of theta. So what we're going to do is we're going to manipulate this equation so we get that occurring on one side. In other words, I'm going to multiply both sides of this equation by the magnitude of u times the magnitude of v, so that I get a dot product showing up somewhere. Because I don't want to have to find the angle between two vectors to find the projection, right? That's going to be never good, right? We should never be trying to find the angle between vectors unless specifically asked to. So what I'm going to do here is I'm going to say, well, great. Magnitude both sides, magnitude multiply both sides by the magnitude of u times the magnitude of v. So on the left side, we have that. On the right side, we have the component divided by the magnitude of u times the magnitude of u times the magnitude of v. Here's what's going to happen. On the right-hand side, the magnitude of u will cancel out. On the left-hand side, the magnitude of u times the magnitude of v times cosine of theta is u dot v. So we're going to rewrite this as u dot v is equal to the length of the projection, aka the component, times the magnitude of v. And then to solve for this, we're just going to divide both sides by the magnitude of v. So it's true that u dot v divided by the magnitude of v is equal to the length of the projection, which is the component of u onto v. Okay. A vector is a length times a direction. We have the length of the projection. All we need is the direction of the projection. What vector also points in the same direction as the projection? I feel like I'm rhyming a lot here. V. So we're going to multiply this length by the direction vector in the same direction as the vector v, or in other words, by the unit vector in the direction of v. So the projection of u onto v is just equal to the magnitude times the direction. It's good to remind yourselves of that fact sometimes. It's kind of I kind of tend to forget it. I'm like, oh yeah, it's just the length times the direction. In this case, it's going to be the magnitude which we just found, which was u dot v divided by the magnitude of v times the direction. It's in the direction of v, but we don't just want to multiply by any length vector. You want to multiply by a unit vector. So it's going to be multiplied by the, and that's not a dot product there. Let's write some parentheses here to make sure that's not a dot product. We're multiplying by the vector v divided by its own magnitude. You could leave it like that. People often like to simplify it a little bit. There's two things you could do. One of them is you could write it as u dot v over the magnitude of v squared, all times the vector v. I'll point out that u dot v is a scalar or a number. So is the magnitude of v squared. So you've got some number times the vector v, which should make sense because the projection is just a multiple of the vector v, right? It's pointing in the same direction, so it should be some multiple of vector v. And then I would prefer to write this as u dot v over v dot v times the vector v. Which I will actually point out brings up something kind of useful, I think. It is true that the magnitude of a vector squared is equal to the vector dotted with itself. For example, if v is equal to the vector, I don't know, sure, 3, 4, 12, just to make it interesting, you could either find the magnitude of v squared as the square root of 3 squared plus 4 squared plus 12 squared. We're squaring it, right? It's the magnitude squared. That's just going to be 9 plus 16 plus 144, which is 169. Or you can calculate v dot v, which not shockingly is the vector dotted with itself. And when you dot the vector with itself, you literally just get each component multiplied by itself. So you get 3 times 3 plus 4 times 4 plus 12 times 12. Same thing. So people will often just interchange these with each other as they see fit, right? Sometimes it just feels more convenient to write it one way versus the other way. So I like writing it this way personally. And I guess what I should really say is, oh, yeah, no, that's fine, is that the projection of U onto V, I would like you to think of it as just the component multiplied by the direction. But then the formula is U dot V over V dot V, all times V. Here's the way I like to think about this when I'm trying to remember what the formula is. Because it's always hard to be like, which one do I have more of? The U's or the V's? Well, basically, whichever one you're projecting onto is the one that you should be in the direction of. And that's the one you should have more of, right? If I'm projecting onto V, I better get a V here. That means all of these other ones, except for that one, have to be V. So the vector you're projecting onto is the one you're going to use a bunch of times. The vector you're projecting to it only shows up once in this particular formula. Great. Let's look at a couple of examples, actually. So let's say, for example, we have U equal to the vector 4, 3, and V equal to the vector 1, 4. Let's find the component and the projection. So, and also let's draw a picture just so we can kind of see what's happening here. So draw a picture. My vector 1, 4 is over 1 up 4. And vector 4, 3 is over 4 up 3. And it's hard for me to tell if this vector is longer than this one, like, or I should say, if the projection is going to be longer or not. So I'm going to just extend this to be safe and say, okay, it looks like we're projecting right about there. It might not be perfect because, again, it's a picture I'm drawing. But this vector here that might be just a little bit longer than V is my projection of U onto V. Let's find the component first, though, just the length. So the component of U onto V, okay, what should I have more of? U's or V's? More V's, right? Whatever you're projecting onto, you get more of. The component part is just the dot product divided by the magnitude of the one you should have more of. I think that's the best way to remember it. The one you should have more of is the one that you're projecting onto. Always more of that one. So in this case, that's going to be U dot V, which is going to be 4 times 1 plus 3 times 4 divided by the magnitude. Why would I pick the magnitude of V? That was a terrible choice. It's because yeah. So, because I made the other choice on the list there. So that's going to be divided by the square root of 4 squared plus 1 squared, which is going to be, let's see, 4 plus 12 is 16 divided by the square root of 17. So my picture is, I don't know, is my picture all right? I don't know. The picture's fine. This component length is a little bit less than 4. I feel like my picture is doing something weird here. That's fine. Sorry, I'm just getting, yeah. So I'm trying to make my picture make sense to me. And I'm kind of like, well, that seems okay, I guess. Yeah. I don't know. I don't love it. It's fine though. The math works. So then that's our component. Let's find the projection. So the projection is just going to, of U onto V is going to equal the same dot product divided by the
v dotted with itself, or just the magnitude of v squared, all times the vector v. So we're going to get, let's see here, u dot v, which is 16, over v dotted with itself, which should be 17, times the vector v, which is 1, 4. So my picture is trash. I see the mistake I made now. Sorry. No, I didn't make a mistake. My scaling's bad. Apologies. So I'll point out this vector is a tiny, tiny, tiny bit less long than the vector v is, right? It's 16/17 as long as v. So my projection, right, this one probably shouldn't have been quite out so far. It should have hit more like there instead. Such is life. Sometimes your pictures don't exactly match up what you're getting. This is it though. That's the whole deal. That's your projection of u onto v. Let's do the better one, which is the other projection, the projection of v onto u. I will point out the projection of v onto u. The picture is going to look a bit different. I mean, it's still going to be the same two vectors, which I'll try to draw better to scale here. Say that one more time. Am I too far down? Thank you. No guarantees here. So let's see. My u vector is over 4 up 3. Still looking like it's probably going to turn out not great. And my v vector is over 1 up 4. So now I'm dropping a perpendicular from v onto u. So there is my projection. Okay. I personally just like finding the whole thing, but I guess sometimes we do get asked to find the component. So let's find the component first. The component of v onto u, again, is the dot product, u dot v, but now there should be more u's. So it's over the magnitude of u. The dot product of u dot v hasn't changed. It's still 16. The magnitude of u is the square root of 4 squared plus 3 squared, which is 5. So the length of this vector is a little longer than 3. Okay, that seems plausible for my picture. Maybe. And then the projection of v onto u, you could just take this component part and multiply it by the unit vector in the direction that we're going, which is u. So we can multiply it by u over the magnitude of u, which is just going to be 16 over 5 times the vector u, which was 4, 3, over the magnitude of u, which was 5. That's going to be 16 over 25 times the vector 4, 3. I don't think there's a good reason to distribute that 16 over 25 there, but you could. You could write it as 64 over 25, 48 over 25. Either way should be fine. I don't find that to be any better than that. In fact, I specifically find this to be better because then I can see, oh yeah, it looks like my projection is 16/25 of the original vector. Okay, that seems plausible from what I've drawn here. And then the last thing we sometimes ask about is the orthogonal complement. This part right here, the orthogonal complement of v onto u. And to find that, we have to find the projection first, typically. And then you say, oh, well, look, the projection of v onto u plus the orthogonal complement of v onto u should add up to the vector v. So if I want to find just the orthogonal complement, or if you prefer the words perpendicular complement, that would be technically acceptable, but orthogonals, right? Orthogonals is another word for perpendicular. We would say, okay, great. The orthogonal complement of v onto u is going to be the vector v minus the projection of v onto u. And then we would actually calculate it, right? Our vector v was 1, 4. Let's write it as 4i. Oh my gosh, let's not write it as 4i because that's not what you want. 1, 4 would be 1i plus 4j. there's your vector v minus your projection, which we just found. And I guess it is good to write it this way here. So my projection is going to be the vector 64/25 I plus 48/25 j. And then I'm just going to subtract the coefficients here. So I'm going to have 25/25I minus 64/25I plus 4j minus, oh, sorry, I should make that 100. So 100/25j minus 48/25j. And so I am getting the vector, let's see, 25 minus 64 is negative 39/25I. And then 100 minus 48 is 52/25j. And that seems plausible because this vector that goes that way is going left, so negative in the I direction, and up, so positive in the j direction. Which seems okay. Or you could write it in the notation I would have been using, negative 39/25, comma, positive 52/25. Either notation should be totally acceptable. Questions, comments, concerns? Okay. There's not a lot else to say about projections. Yeah. Looking at my notes, I'm like, nope, not really. That's kind of it. We could do this annoying question, sure. I can maybe not put all my papers all over the place there. One more projection thing. Here's a question that I've seen in the past. If the vector A is equal to 3, 0, negative 1, find a vector B such that the component of B onto A is equal to 2. And again, I'm just gonna say every time, I really don't like this notation. When I see this, oh yeah, that just means that the length of the projection should be 2. So I'm thinking about my vector A here, looking like this. My vector B could be something like this, where when you drop this down here, whatever you're getting here should have a length of 2. That's what I'm seeing this problem asking me to do. Okay, well, pictures are fine, but let's calculate this here. So the component of B onto A is going to be A dot B divided by the magnitude of A, which is good because we don't know what B is. So hopefully it's right. Also, again, there should be more A's because we're projecting onto A. And that's going to equal, we want it to equal 2. So I don't know what B is, but let's make up just a generic vector for B. So let's say that the vector B is the vector with components B1, B2, and B3. So then when we do A dotted with B, we're going to say that that's going to be the vector 3, 0, negative 1, dotted with B1, B2, B3, divided by the magnitude of A, which is the square root of 3 squared plus 0 squared plus negative 1 squared. And we want that to equal 2. Okay, we can solve this equation probably. So the top is going to be 3 times B1 plus 0 times B2, let's not write that down, minus 1 times B3. All divided by the square root of 10 is equal to 2. So then I would probably multiply both sides by square root of 10. Yeah, would I do that? Sure, yeah. So we get 3 times B1 minus B3 equals 2 times the square root of 10. It looks like there's a lot of answers here. In fact, my picture probably isn't doing it justice because if you look at my picture, you might only think about, well, you could have this vector here, or you could also draw like this one down here. Or maybe I guess this one over here, this one over here. But in 3 dimensions, if you think about a vector like pointing that way, you can kind of have like essentially, let me actually just draw it. You could have like a conical spiral around your vector. So like if you draw like this cone here, it kind of goes around like that, right? You can kind of think of, oh yeah, any vector that terminates on this cone that projects down to the vector at the same length is going to have a component of length too. So there's an infinite number of vectors on that like cone around the centered around the vector that you're projecting onto. So what does that mean for us? Well, basically it means pick a number. So if I'm trying to figure out, let's actually solve for B3 here. B3 is equal to 3B1 minus 2 root 10. So let's make a choice where things don't suck. So let's choose, I don't know, B1 equal to, how about the square root of 10? And then B3 is going to equal 3 times the square root of 10 minus 2 times the square root of 10, which is also the square root of 10. Okay. What about B2? Let's check. Here's our vector. B equal to square root of 10, comma, something, comma, square root of 10. And if I calculate this up here, well, yeah, I'm going to get 3 root 10 minus root 10 over root 10, which is going to be 2. And it actually doesn't matter what the middle component is here. You can pick any number you like. I'm going to pick 7. Totally fine. Right? Check it out. If you put in a root 10 here, a 7 here, and a root 10 here, 3 times root 10 plus 0 times 7 plus negative 1 times root 10 is 2 times root 10, and divided by root 10 is equal to 2. How do I say this the right way? Essentially, it doesn't matter what the middle component is here for this vector because A doesn't have a middle component. So you're essentially drawing A like in the XZ plane. And then you're saying, I don't really care how far to the right or to the left I go because it's not going to change what the projection onto A is going to be. I know it's not the best, I admit fully, but the math works. You could try drawing vectors in Desmos. Yeah, you could. But we got other things to do. Oh, geez. Time just flies on by. Okay, let's start looking at matrices. Yeah. So you should definitely spend plenty of time making sure that you're comfortable multiplying, adding, mostly multiplying, but adding, subtracting, multiplying matrices together. Let's look at a couple examples just so that we're all very comfortable with this. So let's say we have 3 matrices here. A is going to be the matrix 2, 1, negative 3, 5. B is going to be the matrix 4, 0, 1, 3. C is going to be the matrix 6, 1, 2. That is a 6. Negative 1, 0, 1. And D is going to be the matrix 1, 2, 3, 4, 5, 6. And a few things to be aware of. A is a 2 by 2 matrix, 2 rows by 2 columns. B is also 2 by 2. C is a 2 by 3 matrix, 2 rows, 3 columns. D is a 3 by 2 matrix. We can multiply a matrix. So I'll say matrices act a lot like vectors in that you can do the same sort of things with scalars. You can multiply a matrix by a scalar, which is just going to multiply every component by that scalar. So for example, if I want to see what the matrix like 3 times A was, well, that's just going to be 3 times each component, which is going to give me the matrix 6, 3, negative 9, 15. Or if you want to add 2 matrices together, they have to be the same exact size, meaning there has to be the same number of rows and the same number of columns. So the only matrices I could add together here would be A and B. So I could add something like 2A plus 4B, which would be 2 times 2, 1, negative 3, 5, plus 4 times 4, 0, 1, 3. And you end up getting, let's see, 4, 2, negative 6, 10, plus 16, 0, 4, 12, And then just like with vectors, where when you add them together, you add the corresponding components together, the same thing is true for matrices. When you add matrices together, you add the corresponding entries together. So the entry in the first row, first column gets added to the entry in the first row, first column. 4 plus 16 is 20. First row, second column, 2 plus 0. Second row, first column, negative 6 plus 4. Second row, second column, 10 plus 12. But that's not the hard or fun part about doing simplest matrices. The fun part is multiplying matrices together. So to multiply matrices together, what you're really going to actually do is you're going to take the dot product of the rows of the first matrix with the columns of the second matrix. Let's look at an example. Let's find A times B. That's going to be the first matrix. And order is super important here. So unlike most of mathematics you've been seeing so far in your life, where multiplication, the order does not matter, like 2 times 3 is equal to 3 times 2, that is not true when it comes to matrix multiplication. A times B is not the same as B times A, and we'll see that here in a minute. So A times B is going to be the matrix A, which is 2, 1, negative 3, 5, multiplied by the matrix B, which is 4, 0, 1, 3. And here's how it works. It's always the rows of the first matrix dotted with the columns of the second matrix. And kind of neatly, in this matrix, this entry is the 1, 1 entry, first row, first column, the 1, 2 entry, the 2, 1 entry, the 2, 2 entry. Row first, column second. So check this out. When you dot the first row with the first column, you get the entry that's in the first row and first column of this matrix. So in the first row, first column, it's going to be 2 times 4 plus 1 times 1. And then if you use the first row of A with the second column of B, you're going to get the entry that's in the first row and second column of your product matrix. And it's going to be 2 times 0 plus 1 times 3. Again, I'm just taking this row, dotting it with this column. Or if you prefer, this vector 2, 1, dotted with this vector 0, 3. We are literally thinking of the rows and columns of your matrices as vectors. You don't have to think of them that way, but it helps to think of them that way. Same deal down here. Now I'm going to use, so after I exhaust all the columns of my second matrix with the first row of my first matrix, then I move down to the next row of my first matrix. So now I'm going to use the second row. Second row, first column is going to be negative 3 times 4 plus 5 times 1. And then second row, second column is going to be negative 3 times 0 plus 5 times 3. And then we should simplify this. That's going to be 8 plus 1. That's going to be 0 plus 3. That's going to be negative 12 plus 5. That's going to be 0 plus 15. So there's our matrix A times B. 9, 3, negative 7, 15. On the other hand, the product reversed, B times A, shouldn't generally give you the same answer. Occasionally, there are some special matrices where if you do interchange the order of multiplication, you do get the same answer. Those are very special. These are not that special. So I want to point out that you want to be able to do this relatively quickly without writing too much down. So watch how I do this for a second. When I look at this first entry here, I'm thinking, great, first row, first column, 4 times 2 plus 0 times negative 3. I shouldn't even have said the negative 3. I should have said 4 times 2 plus 0 times, it doesn't matter. 4 times 2, 8. Okay, great. First row, second column, 4 times 1 plus doesn't matter. Second row, first column, 1 times 2 plus 3 times negative 3 is 2 minus 9, which is negative 7. And finally, second row, second column, 1 plus 15 is 16. I don't think you need to show the work here unless you want to make sure that you are actually, like, in case you're worried about like your multiplication and addition not coming out exactly right. You should ask questions along the way if you have them. Let's look at, sorry, I lost my matrices over here. Where'd they go? Are they over here? Yes, they are. So I want to point out that you can't always multiply two matrices together. For example, if I was going to try to multiply C times A, where C was the matrix 6, 1, 2, negative 1, 0, 1, and A is the matrix 2, 1, negative 3, 5, I got problems. Because when I tried to do the dot product of this row with this column, I don't have the same number of things. I have 3 things here, and you can't dot a vector in R3 with a vector in R2. Or you can't dot a 3-component vector with a 2-component vector. They have to have the same number of components. So I'll point out that this vector, this matrix here was a 2x3 matrix. This matrix here was a 2x2 matrix. And the way you can tell that the matrix multiplication isn't going to work is if the inner dimensions don't match. Right? Because for this multiplication to work out, the length of this row, meaning the number of columns, and the length of this column, meaning the number of rows, have to match up. So the columns here don't match the rows here. On the other hand, if I was going to multiply A times C, everything is totally fine. A times C, 2, 1, negative 3, 5, times the vector 6, 1, matrix 6, 1, 2, negative 1, 0, 1. Now the dimensions totally work out. This vector matrix. Okay, the reason I keep making that mistake is because later on in linear algebra, you do think about vector spaces of matrices. So it's not inappropriate to call a matrix a vector. I just shouldn't be calling it here. We should just be calling it a matrix. But I'm not totally insane to be saying matrix when I'm saying vector accidentally. So this matrix is 2x2. This matrix is 2x3. The inner dimensions match. Cool. So things are going to work out. Let's multiply it out and let's see here. So let's see. 2 times 6 plus 1 times negative 1 is 12 minus 1. 2 plus 0. 4 plus 1. Done with the first row here. So now I go to the second row. Negative 18 minus 5. Negative 3 plus 0. Negative 6 plus 5. And also interestingly, your resulting matrix has dimensions that are the outer dimensions. So our resulting is a 2x3. And that is always true. If you multiply 2 matrices together, the inner dimensions must match, and the resulting matrix has the dimensions of the outer dimensions. Kind of great. Times it. Okay, not a lot of times. What else should we say here? Oh, and I should have, yeah, no, I definitely will point out again, right? These were not the same, right? A times B was not B times A. They're very different. What else do people ask me? Oh, yeah. So we can also find the transpose of a matrix. So the transpose of a matrix. Written either as A with a capital T as a superscript, or sometimes people use a prime notation. I don't love the prime notation. I think the T is more common, but both are generally accepted. So for example, if the matrix A is the matrix we just had, which I keep, yeah, it's 2, 1, negative 3, 5, then A transpose is just, I always think of it as every row becomes a column and every column becomes a row. The easiest way to write it down is just look at the columns and write them as rows. So my first column is 2, negative 3. That's going to become my first row. My second column is 1, 5. That's going to be my second row. That's the easiest way to do it. If you're for a matrix D, which was the very easy 1, 2, 3, 4, 5, 6, D transpose, same deal. Every column becomes a row. So this column 1, 3, 5 becomes the row 1, 3, 5. This column 2, 4, 6 becomes the row 2, 4, 6. What else? Sure. You can multiply a matrix by its transpose. Always. Always, because the dimensions will always match. So D times D transpose is going to be 1, 2, 3, 4, 5, 6. Generally, when I read a matrix, I read it rows, like I'm reading like a book, like I read from left to right and then go down, right? So I read it as 1, 2, 3, 4, 5, 6, not like 1, 3, 5, 2, 4, 6. That would be a a atypical way of reading it, times D transpose, which is 1, 3, 5, 2, 4, 6. So let's do the multiplication here. And by the way, so actually I should be more kind of, what's what I'm looking for? More transparent. If I have a 3 by 2 times a 2 by 3, I'm going to get a 3 by 3, which is kind of big. Oh, well. Let's see. 1 times 1 plus 2 times 2 is 1 plus 4, which is 5. And then 1, I do like to kind of do this, like this with this, and then this with that. So 3 plus 8, and then this with that. So 5 plus 12. Now moving on to the second row, this with that is 3 plus 8. This 9 plus 16. And then 15 plus 24. And then finally this last one, 5 plus 12. 15 plus 24. And 25 plus 36. Cool. Interestingly enough, when you multiply a matrix by its transpose, you get what's called a symmetric matrix, meaning that this matrix here, let's call it E, is its own transpose. If you took the transpose of this matrix, well, look, all the rows are already equal to the corresponding columns. The first row is the first column. The second row is the second column. The third row is the third column. If you see that kind of matrix, it's not super duper important, but it just seemed like it was a good place to say it. This is equal to its own transpose. We could also multiply it in the opposite order. D transpose times D is going to be 1, 3, 5, 2, 4, 6 times 1, 2, 3, 4, 5, 6. Here we're going to get a much smaller matrix. This one's going to be 2 by 2 because we're multiplying a 2 by 3 by a 3 by 2. So here we're going to get 1 plus 9 plus 25, which is 35. And then 2 plus 6 plus 30, which is 38. And then I should get 2 plus 6 plus 30. So 2, whoa, James. 2 plus 6. Going a little too fast there. Let's try that again. 2 plus 3 times 4 is 12 plus 30 is not 38. It's going to be 44. Sorry about that. Going a little too quickly here. Same deal down here. 2 plus 12 plus 30 is 44. And finally, 4 plus 16 plus 36 is going to be something. It's going to be 56, I think. 4 plus 16 is 20 plus, yeah, that works out. Cool, yeah. Oh, I just called it a new name. So sometimes when you get a new matrix, you just like, I want to call it something. I'm going to call it a new capital letter name. We typically use capital letters for matrices because we do. So I was just like, oh, here's a matrix. I'm going to call it E. And I only did that just to point out that I could say that, oh yeah, this matrix is in fact equal to its own transpose. That's why I wrote that. But yeah, sometimes we just make up a new name when we get a new thing. Is there anything else I can cram in here in the last minute? No, not really. Oh, there was that question though that I totally didn't get to. Sorry about that. Oh, here's actually last thing I'll say. So there are some special matrices that are super duper special. Probably the most important of them are identity matrices. I would actually say there's two different kinds. There's the most important kind, the multiplicative identity. So things like I2 is the 2 by 2 matrix with ones on the main diagonal and zeros everywhere else. I3 is the 3 by 3 matrix with ones on the main diagonal and zeros everywhere else. And it continues on, right? I4 would be a 4 by 4 with ones on the main diagonal and zeros everywhere else. And here's why they're super important. Because when you multiply any other matrix by the identity, it's like when you multiply a regular number by 1. It doesn't change it. So just like 5 times 1 is equal to 5, the matrix A, I forgot what it was, I'm just gonna make up something new, times the identity matrix is exactly going to give you back the matrix you started with. 2, 3 times 1, 0, or dotted with 1, 0 is 2. 2, 3 dotted with 0, 1 is 3. 4 plus 0 is 4. And 0 plus -5 is -5. Hey, look, our A times the identity matrix exactly gave us the identity. So this is the multiplicative identity. Whenever you multiply a matrix by the identity of the right size, you always get back the matrix you started with. All right, I'll stop talking there.